Okay, Chloe, you got a homework question?
Can you do 48?
Okay, maybe one more. Anyone have another one?
30.
We got time for two. So 30 and 48. Can anybody read off? Let's do 30 first. Do you have that in front of you?
xe to the y minus y equals x squared minus 2 with points 2, 0.
Okay, so we want, I'm guessing it says find y prime at 2 comma 0?
Yeah.
Okay. So the idea here again for implicit differentiation is that any relationship involving x and y, all the pairs of points x comma y that satisfy this equation are going to give you a curve. And finding y prime at a particular point is going to give us the slope of the tangent line on that curve. Okay. And I'm going to try this without writing y of x. Okay. I can do it if necessary just to help everybody. But remember, we're really thinking y is a function of x. Okay, so I'm not going to write the function notation. I don't care if you do it on your homework. Just make sure you translate back to y prime and y. Okay, so if I'm doing that, I don't think taking the derivative of 2 with respect to x, that's 0. That'll be 2x. Y is a function of x, so the derivative of this is y prime. So I think really the hard part is, what do you do for this product? Okay, so now again, I take derivative with respect to x on both sides. You don't always have to write this either, but it shows you what we're doing on both sides. And this is again called implicit differentiation. You treat y implicitly as a function of x, and you take the derivative with respect to x everywhere. Okay, so this first one here, that's a product of functions. If you like, x is the first function, e to the y is the second function. Okay, so it's going to be the first function, x, times the derivative of the second. And remember, I'll write it over here. Over here, I'll write the notation y of x, but the derivative of e to a function is the same thing times derivative of the exponent. Okay, so if y is a function of x, it's the first function. The derivative of the second is going to be e to the y times y prime, or if you like, e to the y of x times y prime of x. Plus the second function, e to the y, times the derivative of the first, but the derivative of x is just positive 1. And then minus the derivative of y, or the derivative of y of x, that's going to be y prime. Okay. And then the derivative on the right-hand side is just 2x. Okay. So again, this product right here became this derivative using product rules. I guess I can put a little multiplication symbol in here too. Okay, so again, I'm thinking y is a function of x. I didn't write it this time. So the x times e to the y, that's a product of functions. It's the first function x. The derivative of e to the y is the same thing times derivative of the exponent. And then plus the second function e to the y times the derivative of the first, the derivative of x is 1. And then again, y is a function. So we're doing minus the derivative of y, which is y prime. And then the right side just has x's, so the derivative there would be 2x. And then now we have to solve for y prime. And then just like in algebra, when you want to solve for a variable or a quantity, you keep everything that has that quantity on one side and you move everything else to the other. So I think the only thing I need to do is move the e to the y to the right. And then I have two terms over here. I have this first term has a y prime and this term has a y prime. So what I'll do is I'll factor out the y prime. That leaves me with x e to the y minus 1. And then if I subtract the e to the y to the right, we'll get 2x minus e to the y. So I skipped 2 steps. I moved e to the y to the right-hand side, and then on the left I factored out the y prime. And therefore y prime will equal 2x minus e to the y over x e to the y minus 1. So I'm trying as much as I can to get rid of replacing the y's with y of x. Okay. And then now what you do is you want y prime at 2, 0, so you can write y prime, a bar, evaluated at the point 2, comma 0. We're saying we're going to plug 2 in for x and 0 in for y. So you get 2 times 2 minus e to the 0 over 2 times e to the 0 minus 1. Two times 2 is 4, e to the 0 is 1, 4 minus 1 is 3. 2 times e to the 0, e to the 0 is 1, 2 times 1 is 2, minus 1 is 1, so I think y prime is just 3 at the point 2, comma 0. So you had to use 2 derivative rules on this first term. First of all, that was a product of functions, so I applied product rule. But the second term is really a composition, so I had to use the chain rule. Okay. And then the other one was 48. Anybody have that written? Do you have that written down, Chloe?
Yeah, it's e to the xy minus 2x equals y plus 1. And then it gives you the point 0, 0. And it wants you to find the derivative of y and the slope of the tangent line.
Okay, so find y prime and the slope of the tangent line at 0, 0.
Mm-hmm.
i.e., you want y prime evaluated at 0, 0. I wonder if there's any way for me to make this a little better. That's a little better, but I think what I'll do, let me just move to this other part of the board so we can see this a little bit better. Is everyone okay if I erase this, or? Okay. All right. So again, we have e to the xy minus 2x equals y plus 1. And again, what are we thinking? I'm not going to write it down, but we're thinking of y as a function of x. Okay. So when we're asked to find y prime, y is the dependent variable. Okay, so we're going to take the derivative with respect to x of the left-hand side, and that's got to be the same as the derivative with respect to x of the right-hand side. Okay. So I want to take the derivative with respect to x of e to a product of functions. Right? The exponent has an x and a y of x, so that's a product. So the derivative of e to a power is always the same thing. And then you multiply by the derivative of the exponent. And since the exponent is a product, you have to do first function, which is x, times. And then since y is a function, the derivative isn't 1, the derivative is y prime. Then it's plus the second function y times the derivative of the first, which is 1. So you just get e to the xy, and then in parentheses xy prime plus y. And then how about the derivative of the minus 2x? That should be easy, right? Okay. So I'm really just using product rule and chain rule here. Once you realize that y is a function of x. Okay. And then the right hand side, well, the derivative of 1 is 0, and the derivative of y with respect to x, well, that's just y prime. Okay. And then I think was really just getting to this step maybe the tough part, because after this it's just algebra. You multiply this out, get y primes on one side, get other stuff to the other, solve for y prime, and then once you have y prime you plug in 0 for x and 0 for y. Okay. I think I probably have time to do it, so although at the same time I don't want to do too much for everybody. So I guess, yeah, I'll at least give you a hint. So you have to distribute the e to the xy through, get the y prime terms on one side, move other stuff to the other, and then the terms with y primes, you factor out the y prime and divide by what's left over. Anybody have a question? Kennedy?
I was just going to say, like, it's kind of the opposite for me. Like, I got up until this point, but I'm just having problems with the simplifying, just since I'm not used to these terms, I guess.
Okay, let me ask you this. You'll probably get mad at me for this, but can you solve this? 5 times 2x plus 1 equals x? I know I'm kind of, but it's really no different. What do? You distribute the 5 through, right? And then you have to get the terms with x on the same side. So I'll go through it. If someone's going to ask to see it, I'll do it. Okay. So is that cool if I just kind of work it out? Okay. So if I distribute the e to the xy times the xy prime, I'm going to put the xy prime out front and do xy prime e to the xy plus y times e to the xy minus 2 equals y prime. Okay. And then what I can do from here is I can move this y prime to the left and get these other two terms moved over to the right. So now I would have, and like I said, if I guess at first it's kind of tough. I guess it takes a lot of practice to realize that, once you get far enough, like, to me, this and this are exactly the same problem. Solving for x here and solving for y prime are the same. But that's probably because I've worked with tons of variables flying over all the place all the time. So for me, it's comfortable. Okay, so maybe we just need some extra practice. Okay, so what I'll do is I'll keep the xy prime e to the xy on the left. I'll subtract the y prime over. And then I'll move 2 to the right, and I'll also move the y e to the xy over. So I added 2 to the right, I subtracted this to the right, and then I subtracted the y prime on the left. Okay. And then now where do I go from here? On the left side, I only have terms that have a y prime appearing.
You factor out y prime and then divide by whatever's left.
Okay, so we factor out the y prime. So I'd have x e to the xy left in the first term and just minus 1 for the second. On the right I have 2 minus y e to the xy. And then Nathaniel, I think it was you just said divide by this leftover stuff. And there would be your y prime. And then you just plug in 0 for x and 0 for y to get the tangent line at the origin.
You plug in just both of them into the y prime equation.
Yep, because now what we want is we want the derivative at the point 0, 0, and then you just plug in 0 for x and y. Is there anybody that did not receive a handout yesterday? Jordan, can you give one to Missy for me? But yeah, that's one thing that's hard. Every time you go up a level in math, the amount of extra variables floating around always usually increases. But one of the things that you kind of need to do to maybe help you is realize that none of the algebra rules have changed. They're all the same algebra rules as before, but yeah, it gets a little bit maybe disorienting when you have all these variables all over the place. So we good there, Kennedy? You kind of see how
Yeah.
I did that there? Everybody else all right? Okay. All right. So we have like 30 minutes here, maybe actually 15 and 20, so 35. I went through the first example yesterday, and it was kind of an abstract related rates question. We didn't really know what the quantities x and y represented. T is supposed to represent time, but we didn't really know the units. Okay, so let me read the note on the front page one more time. So in a related rates problem, we'll be given an expression involving certain quantities. In our next example, right, the revenue is a function of the number of units produced. So you have two quantities there, revenue and number of units produced. So one thing is, over time the revenue is going to change, and over time the number of units produced is going to change. Now, even though the variable t does not show up in the function itself, you can still talk about how these quantities change with respect to time. So every variable that appears, we're going to assume that it's a function of t, just like here we assumed y was a function of x. Okay, so really we're still just implicitly differentiating in this related rates section. Okay, and then if you look at the definition, step 1 for us doesn't make a whole lot of sense. Okay. In other calculus classes, where you have physics examples, there's usually some geometric shape that you're setting up a formula relating to variables. But in business calculus, there's no geometry involved for a profit, revenue, or cost function. There's no picture we can really draw. So step 1 in the definition, sketch a figure if helpful. Well, there's not really a figure you can draw. And then step 2 is you identify all relevant variables, including the given rates and the rate that you're trying to find. Okay, so usually there's two variables. You're told how one variable changes, and your goal is to figure out what the rate of change of the other one is. Step 4, we also don't have to worry about step 4. Okay, again, there's no geometry. We don't have to set up any equations based on geometry. You're just going to be given the equations, the profit, revenue, and cost function, or the demand price equations. And then step 5 is once you have your equation, you implicitly differentiate with respect to time. You have to use the chain rule, product rule, quotient rule, wherever appropriate. And then once you take that derivative, you'll be able to solve for the unknown rate. Okay, so what do I mean by all that malarkey? Is it okay if I erase here? Okay. And like I said, I think this might require some more time and effort from before, just because it's such a different process of taking derivatives than we saw in the first so many sections. So example 2, a company manufacturing flash drives, the cost, revenue, and profit are given by these equations. So the cost of producing X flash drives is your fixed cost of $5,000, and I'm guessing it only costs them $2 per flash drive to produce. That's where the 2x comes from. You have the revenue in selling X flash drives, which is 10x minus 0.001x squared. And then the profit function, we're not actually even going to find the profit function explicitly. We're just going to use the idea that the profit function is always revenue minus cost. Okay. And then what it says here, X is the number of flash drives produced in a week. So essentially these are weekly cost, revenue, and profit. Okay. Now, what it says, the given information that tells us the rates and the production levels, it says production increases by 400 flash drives per week. So that's the given rate. You're told how much the quantity X changes over a week period of a week. And that's when the production level is at 400 flash drives. Right, so what you need to be imagining here is that at some moment in time, you've produced 4,000 flash drives, and every week you're going to produce an additional 400 at that production level. Right? So a week later, you'd have 4,400 flash drives that have been produced. Okay, and then it says, find the rate of increase or decrease. I should have really put or decrease, depending on what happens, per week. And we're going to do first cost, B we're going to do revenue, and then C we'll do profit. I've kind of run out of room. Is anybody going to get mad at me if I write these a little bit smaller? I'm going to guess not. And then lastly, I need to know that X is the number of flash drives produced per week. Now, we have basically 4 different quantities: cost, revenue, profit, and then X, the number of flash drives produced per week. Now, explicitly, there's no time. You don't see the time, right? There's no T anywhere. Okay, so we're implicitly, and also this is how it works in reality, quantities change over time as well. Right? The number of flash drives I produce might also depend on time. Right? Next week I'll produce this many, the week after that I produce this many. Okay. We're not going to be able to find functions of these variables with respect to time, but we do know the rate of change. Okay, so if you go back to the definition again, we're supposed to find an equation connecting the variables. Well, that's already given to us. Okay. Step 3, you're supposed to express all given rates and rates to be found as derivatives, like dx dt, dr dt, dc dt. Okay, so first of all, what I want to point out is it tells us production is increasing at a rate of 400 flash drives per week. Okay, well, what variable represents number of flash drives? X, and the amount of time in weeks would be represented by a variable t. So you're identifying the known rate, so that the rate at which X, the number of flash drives, is increasing with respect to the number of weeks, that was given as 400 when the production level X, this is the next piece, is equal to 4,000. So basically we just know at that production level, okay, the amount of flash drives produced is increasing by 400 flash drives per time, which in this case is weeks. Okay, so that was step 3. I expressed, well, actually I need to write the rate that we need to find. So if we're doing part A, what we want is really dc dt. How much is your cost changing per week? So what we're going to do, I'm going to get rid of the c of x part. There's the relationship that relates my cost to the number of units produced. We're going to take the derivative with respect to t on both sides. Okay. So what I'll do now is I'll do the derivative with respect to time of the cost equals the derivative with respect to time of the right-hand side. So this is just like implicit differentiation, where we're treating both variables as functions of t. So c and x are dependent on t. Okay. since I've already converted all my information into symbolic form, I'll get rid of this. Now, this one's not too bad. The derivative of cost with respect to time, one way to write that would be C prime, but it's just a convention that we don't write the prime notation. We're just going to write dc dt. Okay, so the left-hand side is just dc dt. That's the rate of change of cost with respect to time. And then the right-hand side, well, 5,000 is a constant. Okay, so the derivative of that would be 0. And then over here, the derivative of 2x is going to be 2 times the derivative of x. And again, if you need to, I could have written c of t and x of t, right, to see that they're functions. But the derivative of 2 times a function is going to be 2 times the derivative of that function with respect to t. Okay, so the derivative of 2x is 2 dx dt. If you like, it's 2x prime.
But we can't write it like that.
I don't care if you do, just make sure you write it back in this fraction or quotient form. Reason being is, when you read the question help, you're not going to see primes anywhere. When you go watch videos online, nobody uses primes. So I think it's just better that we get comfortable using the dx dt, dc dt notation. Okay? And then actually this is even easier than some of the implicit differentiation problems, because now all I need to do is, at the production level of 4,000, I already know dx dt is 400. So the rate of change of cost with respect to time at a production level of 4,000 is really just 2 times the rate of change of the number of flash drives produced. And I can write, this is 800, and we can write dollars per week. That's another reason why this notation is helpful, because change in cost is given by dollars, and the change in time is given by weeks. Okay, that's why this notation is generally more helpful. So let me pause for a second. I just want to make sure everybody understands the math before I kind of interpret this quantity. Okay, so you're always given a rate. You might be given a production level or some value for a variable. And then I had, in the case, if I know how much the production is changing per week, my goal is for part A to find how much cost changes per week. And then you take your relationship between cost and the number of units produced, and you take derivatives with respect to t on both sides, where really you're really treating c as a function of t, and you're really treating x as a function of time. So right, if I'm doing the derivative with respect to t of c, it's really c prime of t, and another notation for c prime of t is dc dt. I don't care if you write that, actually, that'd be okay. Right, if you want to write c prime of t, that's okay, because at least there's reference to an independent variable. Okay. So yeah, if you wanted to, if it helps you, I don't care if you put the of t's in there. Okay. And then the derivative with respect to t of c is c prime, but you can rewrite that as dc dt. Okay. And then the derivative with respect to t of 2x of t is this 2 times x prime of t, and x prime of t is just the same as dx dt. Okay. So it's just implicit differentiation where all variables are dependent on a third variable. Okay, and then what does this mean? It means if you've already produced 400 flash drives in a given week, right, a week later, your cost is going to increase by $800. So whatever your cost was at the production level of 4,000, right? If another week elapses, your total cost would have increased by $800. Okay. So if you know the rate of change, if you know how much flash drives are being produced per week, that'll tell you how much additional costs you would have per week. Okay. And then we'll do the same thing for revenue. I think that profit's really the easiest, but we'll do that in a second. Okay, so now what's the relationship for revenue? The revenue R is really 10x minus 0.001x squared. And if you like, if it helps you, we're now just thinking of revenue as a function of time instead of function of units. And if it helps you, the number of units produced is now also being thought of as a function of time. So what am I going to get? So I'm going to, I'll skip this d over dt part on both sides. So on the left, the derivative of r with respect to t, that's dr dt, or r prime of t if you like. Okay. And then what about the derivative of 10x?
10x.
That's 10x prime, or instead we can write
10x, or 10 dx dt.
Yep. Perfect. Thank you, Ollie. So you can do 10 times dx dt. Sorry, I was a little off here. Minus, now this one's a little trickier. I think I might come do this term on the side. And I think I'll do it with x prime just to help everybody. So this term can be thought of derivative with respect to t minus 0.001. I'll write in the x of t with the square on the outside. Okay, so we're thinking of x as a function of t. So the constant multiple rule says the minus 0.001 can stay out front. And then how do you take the derivative of a function to a power?
Subtract the power by 1 and then multiply by it.
Okay, so you bring the power out, multiply by 2. The inside stays the same. You said reduce the power by 1. But you always have to multiply by the derivative of the inside, which is x prime of t. And then just replace x of t with x, and x prime of t with dx dt. So I have a minus 0.002 times x times dx dt. When I simplify that. And then finally, if I want dr dt, when the production level, we've already produced 4,000 units, right? How much is my revenue going to increase or decrease per week at that production level? And this is going to equal 10 times, well, did we know dx dt? That was the given rate. We're producing 400 flash drives per week when we're already at a production level of 4,000. So it's 10 times 400 minus 0.002 times x. X is the production level. We're producing 4,000 units. And then we have another dx dt, which is again a times 400.
Isn't it 2001?
Oh, but I had an x. So the 2 came out front, and 2 times 0.001 is where I got the 0.002.
Okay.
Yep. And then let's see. This is essentially going to be 1, 2, 3. 2 times 4 is 8. 8 times 400 is 3,200. 4,000 minus 3,200. Someone check me, but I think that's going to be 800.
Sure is.
I'm not smart. I've just done that 8 million times.
Still impressive.
You want to know what the trick was? 4,000 is 4 times 1,000. The 1,000 brings the decimal to the right to give me a 2. 2 times 4 is 8. 8 times 400 is 3,200. And that's 4,000 minus 3,200, which is 800. All I'm doing is kind of, I guess it's magic, right?
Yeah.
Gymnastics. Okay, and then what are my units again? Here's why I like the dr dt notation, because revenue is in terms of dollars. And
Time is in weeks.
time is in terms of weeks. So interestingly, your costs and revenue are increasing at the same amount per week when you've already produced 4,000 flash drives.
So you break even?
Exactly. Right? That means that when you're produced 4,000 units, a week later, you're not going to get any additional profit. Okay. So we'll do part C because that's the easiest one because we've already put in a bunch of hard work. Because now if I want to do part C, I'm going to write it this way. Profit is just revenue minus cost. And if I take, so if that's P of T, R of T, C of T, if you take the derivatives on all sides, you just get dP dt is the rate of change of revenue over time minus the rate of change of cost over time. Okay, and then dP dt at this production level of 4,000, well, since these were the same, they were both 800, so however many units you produce in that next week and sell is going to lead to no profit, no change in profit. Which probably isn't good for whoever's doing this. Probably have to do some initial analysis of this. You might need some additional information to do further analysis. But yeah, revenue and cost are both increasing at the same value per week, so naturally your profit would not change at all per week at that production level. And then before we do the next one, let's just talk about timeline. Tomorrow there's going to be a quiz over 3.3, 3.4, 3.5. For the implicit differentiation, I'm probably not going to give you one that's too crazy because your time is limited. So I'll probably pick one that is pretty algebraically simple to solve for y prime. And then for the product rule, quotient rule, chain rule, for the quiz, you won't have to simplify derivatives for the quiz. And mostly on the test, which is going to be next Wednesday, most of the derivatives I ask you to take, I will say, please do not simplify. There will be I'll make you have to just simplify one derivative. Again, you only have 55 minutes or 60 minutes, so I can't have you simplify all your derivatives. Right? Okay. So I've been posting practice problems from each section that I think would be good practice. I'll post some problems from the review. I might keep it, there's probably like 40, 50 good problems in the review. I'll probably try and do like somewhere between 10 and 20, just to kind of maybe pick some problems that would best represent what a test would cover. Okay, but maybe a couple extra ones. So yeah, and I don't know if you've heard my spiel, I generally don't like practice tests because I feel like it pigeonholes me. If I give a practice test and I make some of the questions different, has that practice test really prepared you that well? I've had students complain all the time, oh, your test was nothing like the practice test. Well, if it was, would it really be a test anymore? So that's kind of my theory on it, but I will try and at least focus the review just a little bit more. Okay. Anybody decide if they want me to come in this weekend at all?
What day is the test?
It's on Wednesday. So tomorrow we'll do the quiz. I'll start elasticity of demand. Okay. So that's called price elasticity. So that tells you how sensitive the demand is to changes in price. It also tells you, once you calculate your elasticity, you'll know if your revenue increases or decreases for small changes in price. Okay, and we'll finish that up on Monday. Tuesday will be review. Wednesday will be the test. Okay. All right. So one more of these. I think the next one's going to be a demand price function or relationship. And as far as the test goes, I don't know if I'm going to do implicit diff on the test. Maybe one question at most. Okay, but you can guarantee a related rates question in the business or economics realm. So there will either be one kind of like we just did with profit, revenue, cost, or you can expect a question that's going to be similar. Like you might have an equation that gives you a relationship between units demanded and price. So there will be one of those related rates problems. Okay. All right. So let's see what it says here. So the number of units demanded in millions X is related to the price P in dollars by this equation. I think we've probably seen this thing like 5 times now. So poor road conditions during shipments are driving the price up $2 per week. Okay. Find the rate at which demand is changing when the price is $40. Okay, so you have the relationship between the variables. We're going to treat X as a function of T. Price is also changing over time. Okay. So there's this third variable, time, floating around in the background. We don't know how these are depending on time, we just know they are. And then you're given the information about one of the rates. So if poor road conditions during shipments are driving the price up $2 per week. So that's telling me about a change in price over a change in time. And it says the price is being driven up by $2 per week. Okay, so the change in price over time is $2 per week. The question says, find the rate at which demand is changing over time when the price per unit is $40. Yeah, that's fine. Okay, so you have you have a relationship between variables. X and P are implicitly functions of T. Okay. You're given the rate of change of one of the variables with respect to time. The question says find the rate of change of demand with respect to time. Okay. And then you're given a particular price level, $40 per unit. And then now the next idea, or the next goal, is to differentiate both sides with respect to time so that these rates will show up. This is why it's called related rates, by the way. Once you have an equation relating the variables, you take a derivative, and that gives you an equation relating the rates. Okay, so that's the whole idea here. Where's my disoriented? Okay, so again, if it's really helpful for you, go ahead and write x of t, p of t, and then you can start by at least writing x prime of t and p prime of t, and then by the end, make sure you switch to this dp dt notation or dx dt notation. Okay. The prime notation is what's called Newton notation, and this dx dt is what's called Leibniz notation. Newton and Leibniz, I think they're around in like the 1600s or 1700s, and they both independently developed this theory of calculus. Okay, I think Newton's goal, he was more like physics orientated, like he was trying to solve physics problems. I don't really know what Leibniz's motivation was for trying to develop calculus, but anyways, so that's the difference in notation. The prime notation was just what one mathematician came up with. This other notation is what a different mathematician came up with. There's certain contexts where prime notation is more helpful, and there's contexts like related rates where this notation is more helpful. This is certainly more helpful to get the units on the rate of change. All right, so what we're going to do, I'll just write this on both sides this time. And then what do we know about radicals again? We always convert to fractional exponents. So instead we can write, let me do brackets here. We can do 5,000 minus p squared to the 1/2 power. Now, the left side's the easy one, because the derivative of x with respect to t, well, that's just dx dt. The right-hand side's the more challenging one. We have to use a combination of two derivative rules. Because we have a function to a power, we have to use the general power rule. But then when we take the derivative of the inside, we have to use the chain rule on the p squared part. Well, oh, sorry, that's also still just the general power rule. I keep saying the chain rule is the general rule. When you have a function to a power, the chain rule is just called the general power rule. Okay, so what do? You bring the power out front. The inside always stays the same. Subtract 1 from the power. And then again, if you want to see it, I can write it over here. But if you're thinking of taking the derivative with respect to time of p of t squared, that's really what this is here. It's p of t squared. The power comes out front. The inside stays the same. The power becomes 1, and you multiply by the derivative of the inside. But in our notation, this would be 2p dp dt, if you need to convert back. Again, it might be helpful to think of p as a p of t instead of just p. So I have to multiply by the derivative of the inside. It's going to be minus 2p, so I have this extra minus out front. The derivative of 5,000 was 0, and then we multiply that by p prime or d prime dp dt. Now, what was the known quantity again? Oh, they were nice to us. It's nice they gave me dp dt first. Okay. If I knew dx dt first, we'd have to solve for the dp dt. It'd be more work algebraically. Okay. Alright, so I want dx dt when the price is $40. Okay. So when you're selling your units for $40 per unit, right? How much is the quantity demanded changing per week? So what I'll write is dx dt at a point when the price per unit is $40. And then all I have to do on the right-hand side is plug in 40 for p, and the dp dt becomes 2. So I'll do 1/2 5,000 minus 40 squared, the minus 1/2 times negative 2 times 40 times dp dt, which is 2. And there's really no need to simplify here. I'm not trying to figure out where the rate of change is 0 or anything. Since I'm just trying to find a rate at a particular value, we can just leave the right side as is and plug in all the values in the calculator. That's not good. I bumped this. Alright, so I'll plug all that messy stuff into the calculator, if I can find my calculator. 0.5 times, parentheses, 5,000 minus 40 squared, parentheses to the minus 0.5 power, times negative 2 times 40 times 2. To 2 decimal places, I get minus 1.37. Anybody else get the same thing?
Yeah.
You did, Nathan? You did, Ollie? Okay. Now, what are the units? So, dp dt is dollars per week. This is change in units demanded per week.
Oh, millions of dollars per?
So again, that's number of units. Only the change in price has dollars of units. Right? This is the change in the units demanded over time.
So units per week?
Yeah. So units per week, although you have to be careful because read the very first sentence. X is not really, it's in terms of millions.
Okay.
Yeah, if you read the very first sentence, it says the number of units demanded X in millions.
Millions of units per week.
Yeah, so this is million units per week. So what that means is, I mean, that's probably not good. Your demand is decreasing quite a bit. So when the price is $40 per unit, a week later, you can expect the demand to decrease by 1.37 million. Is it basically time? Did I steal time? I did, I stole a minute. Okay, so tomorrow we'll start elasticity. We'll do a quiz. I'll try and make it reasonable, like maybe 15, 20 minutes tops. Make sure you review your product quotient and chain rule, and maybe make sure to look at a few implicit differentiation problems.
And the homework. So, actually, I understand how you substituted dPdt, but how do you get the negative 2?
Oh. So, if I'm taking the derivative of 5,000, that's 0. But if I want to do the derivative of minus p squared, it's minus 2 times the inside times the derivative.
Okay, 2 questions. So like the limit you said, how can you tell like you were saying about how what you said, like
Oh, but when the units
yeah,
are.
like how can you tell that it's dx? That 2 is, do you know what
So
I'm
this is
asking?
saying
Or for the dt.
this is driving price up.
Okay, so
So
that's
that's
how
telling
you
me
can
how
identify?
price is changing.
Okay.
Yep. So that's why I have dp